How does it work when you are sending some amount of money from one bank account to another and something fails during this operation? The bank account is intact, so the balance is basically as it was before the failure has happened. In order to explain this phenomena, we need to tackle some of the basic but really fundamental concepts in databases world, which would be transactions, A.C.I.D, isolation levels, and concurrency phenomena that basically are based on isolation and the concepts around it. So let's get into it. If you are new on the channel, welcome. I'm Chris. I'm your guide in the data world and happy to go through today with you about transactions, A.C.I.D and isolation levels. Let's get into the topic right now. So transaction, right? It's basically a way or a mechanism, you may call it, of grouping operations into a single logical unit. By operations, I mean here read, write, delete operations, changing state operations of your tables inside of the database. Normally, transaction begins with a begin statement and ends with an end statement. Although when you are working in an IDE of your choosing or in a terminal, you are not necessarily writing each and every single time begin, then your select, then end, and before that commit or rollback, right? Normally, these kind of operations are being handled for you by the IDE or by the way that you are connecting to the database. So the begin end is implicit, it's being done behind the scenes. But it's important to understand that to open a transaction and to close a transaction, begin and end is necessary, right? And the transaction may have one or more operations. So you can have a select operation and that's it, or you can have insert, update, delete, and a select operation as part of one single transaction. In the code snippet shared in this slide, you can see that there are basically two operations. One is basically moving money from account A, and the second one is adding money to account B. So basically a bank transfer between accounts A and B. And it's all enclosed into a begin and end statement. And when the operation is successful, we are committing the state to the database, commit operation. But if something bad happens, some failure happens, we are doing basically a rollback operation. So rolling back the changes as it were before. So does it answer our question from the beginning of the video? Not exactly. And to tackle it in more details, let's get through the A.C.I.D acronym. And what is A.C.I.D exactly in databases world? So it's basically a set of mechanisms, or maybe more specifically rules, for providing fault tolerance. What does A.C.I.D stands for? So the A stands for atomicity, C stands for consistency, I stands for isolation, and D stands for durability. And let's get into those in details. So atomicity, it's basically a way of making sure that an operation or a group of operation will either succeed or will fail. There is no in-between state. There is no, yeah, maybe I've inserted this data or maybe not, like with the Schrödinger cats. Maybe it's inside of the box or maybe it's not. No, the database approach to this one is really clear. It's either a success and a commit operation, or it's a failure and rollback operation. Here in the snippet you can see 4 operations, out of which 3 were successful and 1 was a failure. So now the question is whether they were organized in basically a transaction on its own. So all of them were executed as part of the one transaction, or each of them were a separate transaction. The state would differ, because basically if this was one single transaction, there was a failure, so the whole state will be rolled back. But if this was 4 separate transactions, each of them will have its own state. So the first one, second one, and the fourth one will be a success. Commit operation will be successful. And the third one will be basically a failure. Moving on, consistency. The database is in good state, period, right? Let's move on. No, let's park it for a second. What does it mean exactly that the database is in good state, and who is responsible exactly, or what is responsible exactly for this good state? So basically it means that you as a developer, or you as a person working with the data inside of the database, or whatever else you are using to save your data, right? You are living, when your operations are finished, you are leaving the state in a consistent manner. What does it mean, for instance, in practice? So let's say you have your bank account and you have $100 on your bank account and you want to send this $100 to your friend, right? So the operation of sending $100 will be successful operation because the account state allows you to do it. You have this $100, and let's not get into the credit line details, etc., right? Let's just assume that you need to have the money to send it, right? So you have this $100, you can send it to your friend, perfect, right? But let's say you want to send $200, but you only have 100, right? So if you are going to send those $200 and leave the database state in, let's say, -100, we might say that the database is in inconsistent state because it's a situation that we as a developers, we as a designers haven't thought about, and it shouldn't even happen, right? So now the question is, who is responsible for it? What mechanisms are protecting us from it? Basically the ones that we are going to code. It can be either a trigger, it can be a stored procedure, it can be a check in your code in the upper layers. So basically, we as a developers are responsible for consistent state of the database of the tables inside of our data world. If we are going to leave the database in inconsistent state, it's on us, but it shouldn't even happen in the first place. So all of the mechanisms that you know that can protect us from leaving the database in inconsistent state, we should use as part of our working with the database basically. Now, isolation. What is isolation? It means basically that two or many other different transactions, when they are working especially in a single object like a single table, are not basically affecting one another. So when a user 1 is doing an update operation and user 2 is doing a select operation, depending when they of course started the transaction, and we are going to talk about it more in a second, but their operations should be successful as long as they are okay. That's first thing. But the second thing is that they should get appropriate results based on the time when they have basically queried the tables or when they issued the operation, when they opened and executed the transaction. So in our case, user 2 executed a select statement to the table movies to get ID 1 and it get a result Avengers, right? So the ID 1 was pointing to Avengers. Now user 1 is basically doing an update to this table and is changing the name to Avengers 2 for the same ID. Then he is doing a commit, so it's basically saving his operation to the database. So when the user 2 will execute the select again, the result would be Avengers 2 instead of Avengers 1. So one transaction did not affect the other one as long as they were mutually exclusive, and we are going to talk about it in a second. Now the durability, the last one, the last principle, the last rule, is basically a promise that after successfully accepting a transaction, successfully executing a transaction, the data will be saved in the storage of your choosing and will not be forgotten, regardless whether there were some failures, something bad situation, emergency situations that were happening. What does it mean in practice? It means basically that we are storing the data of our database structure in general, and something bad happens. Database is restarting. After the restart, we are getting back the same state as it was before the failure happened, basically. And it's really important because otherwise we would be constantly having problems with the state of the database that was not matching what we've saved it. And it was really important in the early days of working with the databases when we didn't have such robust mechanisms as we have right now. We didn't have such robust storage ways of storing data as we have right now. Currently we have SSDs, hard drives, replication, constant backups into multiple regions, clouds, etc. Right? So there is a ton of ways of making sure that the data of the database is basically stored securely, and even in case of something bad happens, we can easily get the state to how it was just before the emergency happened. So this was the A.C.I.D basically rules. Now, to understand better and to basically explain fully the case from the beginning of the video, so the operation of moving money from one bank account to another, we have something that is called concurrency phenomena. And this is strictly related with isolation, and the way that this concurrency phenomena are being handled will be basically really strongly connected with how your database of choosing is handling those phenomena. There will be 4 different isolation levels that you can use in order to solve those phenomena, and some of the databases are using one, or you can select which one you would like to choose based on your current operations. But in general, let's walk through all of them and see, and let me explain you the details of those. So, phenomenon number 1, called dirty read. So we have 2 transactions basically, and the state of the initial table, the database state, we have a table called sales ID 1, sales amount 500, right? Transaction 1 is being opened and transaction 2 is being opened right after the first one, right? So in transaction 1, someone is basically doing an update operation to this ID 1 and changing the amount from 500 to 100, right? Now, the second transaction is doing a select statement for this exact record with ID 1. What will be the result? The result would be the sales amount 100. Should it be? This depends, right? Because both transactions are in progress. There was no commit, no rollback. So let's assume that right now the transaction 1 is doing other operations and something fails during these operations. So the state of the database is rolled back, from sales amount is changing from 100 to 500, and the database state is back into 500, right? But the second transaction, transaction 2, is still happening. So someone is changing this record with ID 1, and maybe in that point in time, this transaction is changing wrong value. So the value is not 100 actually, because the transaction was reverted, but it's still 500. But we might get improper results because of this one. This case is called basically a dirty read, when we are reading some information that was not saved properly into the database. Moving forward, phantom reads. Again, same scenario. Currently, the only difference is that we have 3 records in the database: sales, ID 1 to 3. Sales amount is not really important. What is important is that transaction 2 is opening, is beginning the transaction and doing a select. In this select, this transaction is getting back 3 results, 3 records, right? And right after that, second transaction is starting, transaction 1 here, and is doing an insert operation. So there is new record, ID 4, sales amount 900, and is doing a commit operation, right? So the information is saved into the database. It was successful, right? But then getting back, the transaction 2 is doing it hasn't finished the transaction yet, so it's still in the transaction. The previous operation was not yet committed. There was no commit operation. But again, this transaction is issuing the select for the same information. Let's say, get me all of the records from table sales. Now, what should happen? Again, depends on your isolation level. It can happen that A, you will get only 3 records, so the same amount of records that you started the transaction with, or how it is in this case, in case of phantom read, you are going to get 4 records. So your database states, so the table state basically changed between one select operation and another select operation in the same transaction. So there was no commit, no rollback here. The transaction is still ongoing. Let's say we made a select, then update, insert, whatever, executed some stored procedures and doing the same select again. So we would expect the same state, but it's not in this case. And this may cause some problems, like when we are calculating some analytical queries, like calculating the counts, making sums, etc. It might be problematic that the state was different than we started the transaction with, especially when the transaction is still happening. Phantom read. Non-repeatable reads, friends. So database state, again, sales, 1 record, ID 1, sales amount 500. Transaction 1 is starting the transaction, opening the transaction, and again, simultaneously, transaction 2 is starting and doing a select. So transaction 2 state is that we have this 1 record with the sales amount value 500, right? And while this result was provided. Transaction 1 is updating the state of record ID 1 from 500 to 100 and committing the transaction. So the database has a new state, which is basically sales amount 100. But again, transaction 2 is inside of the same transaction. So there was no commit, no rollback operation here. It's just basically issuing the same select again for the same record. It started from sales amount 500, but right now the sales amount is 100, right? So from the perspective of the transaction 2, the state has changed even though the transaction was still in progress. And again, this may lead to some problems because let's say we have a bank account, we started the transaction and checking the values. So the state of the transaction, so state of the bank account was 500 when we started the transaction. Now we want to make a payment and we are checking, okay, can we make a payment for $200 from this account? Yes, because the state is 500, right? Okay, let me start. And some operations are executed, but then when we are actually executing the operations, yet again, the state is not 500 anymore, but 100. And that may lead to some serious problems, right? Non-repeatable read in this example. And last one, lost update. Same story, we have a table sales, ID 1, sales amount 500, and 2 transactions. So in first transaction, we are basically doing an update operation to the same record, ID 1, we are changing the value from 500 to 100. But then the second transaction is also updating the same record, ID 1, but from basically the new value would be 900, right? And you can see here that the first update was done by, transaction 1, the second update was done by transaction 2. Transaction 1 is committing the operation, leaving the database state in a sales amount 100. But then transaction 2 is actually doing commit after the commit was issued from transaction 1, and the database state is changed from basically 100 to 900, right? But what has happened in between? We've basically lost an information that there was a state of where the sales amount was 100, especially for the transaction 2. So transaction 2 was not aware at the point of time that there was a state change from 500 to 100. Let's say that this was basically, it was not simply an update set 900, but it was an operation of take the current state of account and do plus 100 or plus 200, right? In this case, plus 400, right? But you get the idea. So get the state of the account and add $400. And in this case, it would be, the result would be 900. But in the meantime, someone else changed the value from 500 to 100. So at the end of the day, we lost basically this information. And again, we are leading to inconsistency in the database, right? So how to solve these problems, how to solve these 4 concurrency phenomena, how to solve these issues, how databases are dealing with those. Databases are dealing with those by using isolation levels. And we have 4 different isolation levels that we can use. Check your databases, whether this is SQL Server, Postgres, SQLite, whatever, how your database is handling isolation levels, what is the default isolation level, whether all of them are allowed or maybe just selected ones are allowed, or if you can basically do isolation levels on your transaction level or this is database level. In general, the concept is as follows. What is allowed to happen inside of any of those isolation levels? So when the isolation level is set to read uncommitted, basically any of those problems that we've mentioned, dirty reads, lost updates, non-repeatable reads, phantom reads, are basically allowed to happen. So any of those 4 can happen. When read committed is selected as isolation levels, dirty reads are not allowed to happen. But lost updates, non-repeatable reads, phantom reads can occur. Repeatable read, in this case, only phantom reads can occur. And in serializable isolation level, we are protected with everything. So neither delete reads, lost updates, non-repeatable reads, nor phantom reads can happen. Okay, so you may think that's perfect. So let's use every time and for everything serializable. Well, it depends, right? So with increasing the isolation level, you are basically adding more and more checks for the database to do in order to execute the transaction. So it may lead to basically more checks, may lead to longer periods of accepting the transaction. It doesn't mean that your transaction will now take a couple of seconds instead of milliseconds. No, it's not like that. But especially in the transactional systems where millions of transactions can occur every second, it's really important to understand the differences in isolation levels, and in some cases accept that, okay, we are going to select repeatable read as an isolation level. We are fine with the phantom reads, but we have our ways of handling those. But thanks to this one, we are actually gaining some performance speed, some improvements, instead of basically using why we would have the same when using serializable. So it's always a trade-offs between one another, but it's, again, at the end of the day, the trade-offs that you need to think about in order to make a good and well thought decision, right? So today we've tackled the fundamentals, as I said, of the databases, but these fundamentals are crucial because right now when you are going to think about the transaction, I hope that you are going to think about all of the things that may happen behind the scenes. So when you are doing a select, someone else can do insert or update or delete. And behind the scenes, what I haven't mentioned, but this would be in another basically time, you might lock the table, so another person will not use it because you are doing some operations, and this will prevent those things to happen, those dirty lost updates, etc., right? But it all comes down to isolation levels selected on your database and the way that you structured the transaction that you're basically executing. In case of any questions, let me know. Happy to discuss those. And for today, that's all. Thank you. See you next time. Bye-bye.